Now, I sent you that. I sent you that polar grid graph. You're gonna want to use that. I'm gonna put it on your quizzes. I'm gonna put it on your tests. So it'll all be labeled. I'm not. It doesn't need to be a big secret how to, label a polar graph. It's fine. You know how to do that. So for the first exercise is on page 238. We're just gonna plot some points just to kind of get you back into the place of doing that. Remember that polar coordinates come in this form. With the first coordinate is the r, the radius. The second coordinate is theta. And we're only going to be doing things in radians, okay? So on this grid, I want you to plot these 4 points. And you can put them all on one grid. As you'll see, I have different colors for each point, and then I labeled each point. That's important when you do put things on one grid, more than one thing on one grid, be sure to label each of those points. So go ahead and do that, and we'll just make sure we're good on that. So the question, of course, the discussion now is about D, and so I'm just going to put the answers up there, and then we'll talk about them. Okay. Here are... Here are the 4 points. Hold on. Your points are right. Good. Yeah, you don't have to draw the lines, but you can draw the lines. Okay. So, in the one thing that I found as I've been creating all these presentations is that I wish they made the circles. I wish they got rid of half the circles. Like I wish this was 1 instead of this being 1, and I wish this was 2. I wish there's a little more room, but it is what it is. It'll help us later. But let's go to D, right? Because
wait, can we look at C?
You want to look at C?
Yeah.
Sure. Oh, you want to know what the angle is over here?
Yeah, I just.
Yeah. Okay, so this is 7 pi over 6 for C. So here's what we end up doing. Okay, since the radius, since r is positive, okay, you could think of it one of 2 ways. One, you could go, all right, I'm going to go from 3, and I'm going to go clockwise minus 5 pi over 6. Okay, that's probably the best way to think about it. However, since this thing is not labeled in negatives, you have to kind of work it backwards, right? And so maybe you're going, all right, here's a pi over 6, so I'm going 5 of these. There's another one over here, and then you keep going until you get to 5. The other way you could do it is think about it sort of complementary, right? What is a reference angle, a positive reference angle, that's going to land in the same place as negative 5 pi over 6. And that's just a matter of adding 2 pi or subtracting 2 pi. Every rotation around is going to land me in the same spot. So if you add a 2 pi to this, you're going to get 7 pi over 6. Okay. Right? And so that's where this should be. That's another way to think about it. Now this one, what's interesting when r is negative, so what you do is you go, all right, let's just go to 2, 3 pi over 2, right? And that puts me here. But the negative says, no, flip it around, go 180 the other way. And that might be kind of the best way to think about it. If it was positive, we'd be here, but since the radius is negative, we just go 180 degrees the other way. Okay, and we're going to talk about that more here in a minute with some other problems. Maybe you didn't know that, maybe you didn't remember that, but that's what happens. It sort of flips it. It takes the radius and it reflects it. That's kind of the best way. Okay, you'll do some of that today. Okay, that's fairly easy. I'm pretty excited about my presentation because I have some more graphics. They're pretty low-level graphics. And you don't have to laugh at me, it's fine. I like my little low-level graphics. And they change a little bit. You'll see. This one's gonna go fine. Ready? Are you ready for this? Are you ready to be super underwhelmed? Oh, thank you for the drum roll. Wow. Converting between polar and rectangular. In either direction. You like it? Thank you. Appreciate it. Now we're only gonna do one at a time. So the first time, the first one we're gonna do is from rectangular to polar. Just one. All right. So this is example number 2. I know it's the small little victories, I guess. So we've got this rectangular point, meaning this is x, -1, this is y, square root of 3, and we're going to put it into polar form, as you can tell by my GIF. It's not GIF, by the way. GIF is a peanut butter. GIF is, no, it's GIF. It's definitely GIF. GIF is peanut butter. Anyway, we have 3 possible situations that we're going to look at. There we go. Froze all of a sudden. Okay. One, I want you to come up with a polar point that r is positive and theta is positive. Then we're going to come up with one where r is positive and theta is negative. And then we're going to come up with one where r is negative and theta is positive. Now, I'm going to do the first one with you because it's been a while, and I'm guessing you don't remember what to do, and that's okay. When we deal with polar coordinates, there's 2 main, I guess, formulas that you're going to need to use pretty regularly. The first, the idea that x squared plus y squared equals r squared, and that's just Pythagorean theorem, right? When you learned about basic trig functions, we had to talk about x, y, and r, and y over r, x over r, y over x, that kind of thing. And that's where this kind of comes from. And this is where we're going to start, because when we have a rectangular point, we have an x and a y. And so what we're going to do is establish what r is. And so the first thing that we're going to do is be able to make our determination of r. Then we have to figure out what angle this point makes with the x-axis, where we call it the terminal side, where when we draw from the origin to this point, that's the terminal side, and then what angle is created. Okay, so of course we can pretty easily find what r is. We got to square 1, we got to square y, we got to square -1, and we got to square the square root of 3. So this is 1 plus 3 is equal r squared. So then, of course, what is r? Plus or minus 2. In this case, since we want r to be positive, okay, r is just going to equal 2. Okay. Over here, we'll end up using -2. Okay. So the reason I only wrote 2 is because they told us it needed to be positive. Right. Now, we have options in terms of finding theta, but just to be consistent, since we know for sure, like here's, I guess, it's possible we mess this up. We mess up our math, okay? I believe that we should use the information that they're giving us to just be safest. So since they're giving us an x and a y, in order to find theta, we're going to use tangent, okay? Could you use cosine and sine? Sure you could. Okay, because we know that this is 2. But let's pretend we might have made a mistake, all right? That way we just use that information that they gave us. So what we're going to do to find theta is just do the inverse tangent or the arctangent of 3 over -1. Okay, and then that will give us our angle. Let's go ahead and figure out what that angle is. It's either pi over 6 or pi over 3. Except it's not pi over 3 or pi over 6. Why not? Because it's negative. Because x is negative. So it's got to be a reference angle with one of those. Which one is it? Is it?
2 or 3 quadrant.
Because, okay, wait, all students take calculus.
Oh, that is so smart.
I don't know this. What are you talking about?
So she does all students take calculus. All of them are positive.
What am I doing?
In the quadrant.
Okay, all right. This is good. What?
So this means all the trigonometric functions would be positive in this quadrant. the sine is positive here, everything else is negative, tan is
Oh,
positive.
I don't need this. Yeah, but that doesn't help me figure out which one's
You're one-
which one's 30 and which one's
You already know
60.
it.
Oh, well, it's
You get a
60.
triangle.
Because the triangle, right?
Well, yeah.
So
But-
that's what I'm saying.
So
Like,
did you should you draw the triangle?
Yeah.
Oh, okay. Yeah, no. I'm trying to come up with for my entire life, I've been trying to come up with a way to keep them straight. Which sign is, 1/2 for 30 or 60 without drawing the triangle.
For
Right, but I can't keep it straight. This is what I'm saying. My entire life I can't keep it straight.
always is the y first for the pi over.
See, that's not all students take calculus. I thought you were going to give me a really slick thing, and I was going to be able to keep it straight finally for once in my life. No. I know, you draw it. It's easy. You can draw it.
Imagine it in your head.
I can. Oh, I can do that. But I don't want to have to go through that every time. And I have to go through that every time because I don't want to. I want to just know it. All right, the answer is it's pi over 3, but it can't be pi over 3 because it's got to be in the second quadrant.
So
Okay,
2 pi.
so it's 2 pi over 3, yes. I'm just trying to come up with a way to keep it straight and without drawing the triangle and without having to picture it in my head. Like, I guess I still do it, but for like sine and cosine of 0 and pi over 2, but to me those are easy to just kind of picture. I don't have to draw and go, okay, the thing, so the square root of 3 is over here and the 1's over here. The square root of, the 1's over here and the square root of 3's over there. Like, right? That's what you have to do because of course the 2's the 2. Because since x is negative, it has to be in the second quadrant. And so it's because the y is
Yeah.
positive.
But how do you get to pi over 3?
Your reference angle is pi.
Oh, wait.
Yeah, so the angle it's 60 degrees. And so 60 degrees is pi over 3. And so when I look at how do I get to 60 degrees on the other side to get it close to, it's 120. And so,
Oh, to make it.
make it. Okay. Now we've done the work. Now we have to write the point. Okay, we have what we need. And the first time we do it, so the point is 2 pi over 3. So we know that we're working with 60 degrees or pi over 3 or some variation of pi over 3. Okay. And so what we have to do now is apply that idea to these two. Okay. So now what they're saying is, all right, fine. R's positive, fine, it's 2. It's still going to be 2. But what's a negative angle that is going to be in the same place as this? Because that's not going to change. So keep in mind, the point still -1, that the rectangular point is still -1 square root of 3. So it's still in the second quadrant. Okay, so in other words, if you were drawing this out, right? If you were drawing this out, you'd have something like this, right? That's the same for all 3 of these parts, A, B, and C. It's the same point, okay? But you can express it in different ways. So one way that we've expressed it, if this was polar, is this would be 2 pi over 3. Now what they want us to do is go, all right, fine, give me a positive. Okay, so it's still 2. But what's a negative angle that lands there? And so you'd be like, okay, how do I get from here to here? What's that angle got to be? Very close.
-4 pi.
-4 pi over 3. Okay? And the thing that's nice, yes, you're very close. I did tell you were very close. The idea being, here's another way to think about this, is if you're looking for a positive and a negative angle to land in the same place, they combine to make a full circle. So if you want to think about absolute value, that they just add up to 2 pi. Right? So that might be a quicker way to do it. So you're like 2 pi over 3 is the first one, so the next one's got to be 4 pi over 3, but it's a negative, so it's going the other way. This next one should just be negative 4 pi over 3. All right, now this one I'm going to draw a little graph. You don't necessarily have to do this, but you can, okay? Because since R has to be negative, so this is that reflection, that 180-degree reflection, okay? So this is where my point is right now. Okay, 2 and 2 pi over 3. in order for r to be negative, it's going to have to flip over to here. Okay? And so I'm just going to put the line on there, and then we know what the angle is, because it's still supposed to be positive. And then I just make this -2, and then it flips around, and it's 5 pi over 3. Okay? So you may, for a negative angle like that, you may want to draw it. It's off by how much, though? How far apart are they? It's off by pi, right? We're talking 180 degrees. So it's off by pi. That's another way to think about it. So once you have your positive, just know that the negative radius version is going, the angle itself is going to be off by pi. Okay? And if you want to write that down in your notes, like, hey, this one's off by, these combine, the absolute value combined to 2 pi. These ones are off by 1 pi. However, you know, or you can think through it. I don't care. It's up to you. So just as a reminder, we have a point. This point, they gave us this. All we're trying to do is change it into polar form.
Okay.
It's not going to be a different point in another place. And the reality of this is this is how we come up with this. But if I was to, the arrow's frozen. If you were to graph this, it is not this point. It is this point. Okay, because in reality you go, oh, I go to 5 pi over 3, and there it would be 2. But it's not 2, it's negative. So bing, it bounces back over there. I just drew this so we could see where it would be. Okay, so this point right here is actually 5 pi over 3. I'm going to move that. Let's move this. Because the reality is, it is that point up there. I labeled it. I put the point in the wrong place. This point down here is 5 pi over 3. Does that make sense? Yeah. Because and if necessary, let's do this. Let's see if I can. Yeah, there it is, gone. Boom. Let's go the other way. Polar to rectangular. Okay, and then there's something else that you probably, maybe you don't remember, but I'm going to give it to you. But what x and y equals in terms of polar coordinates, we took, So I'm just going to. So in polar coordinates, x equals r cosine theta, because cosine theta equals x over r. And y equals r sine theta, because sine theta equals y over r. That was, that's algebra 2 stuff probably. I know I teach that in algebra. I don't teach it in this form, but I do teach the x over r and the y over r. Okay. So the key for this kind of problem is knowing that you're going to have some sines and cosines in your answer. Okay. All right. So since what we're trying to do is come up with x and y. And since they're giving us r, they're giving us theta, it's just a matter of plugging those in and then evaluating what x and y would be. Okay, so here's where so x is 2 cosine pi, and y is 2 sine pi. So yeah, I have no problem remembering my pi's, and pi over 2 and 0 and 3 pi over 2, because one of them's 0, and then I just tell you, okay, which one's 0, which one's 1. And in this case, it's going to be negative. Right? So is cosine pi 0 or negative 1?
Negative 1.
Negative 1, which means this one is 0. Okay, so that means x is negative 2, y is 0, and a rectangular point is just negative 2. Now, this example was easy because, of course, the angle was pi. If you have to draw the triangle and you get a pi over 3 over pi over 6 or something like that because you need to do that, then you just work your way through that, and that's not a big deal. Okay? That is part 2. Next one, however, is now we're going to convert equations. So we converted some points. We're going to convert some equations between polar and rectangular. And yes, it's the same gift over and over again now, so it's okay to not be excited about it. Which direction do we go first? we are going to go still from rectangular to polar. So here's a rectangular equation, just a regular linear equation. And we're going to convert it into polar form. Here we go. So we start with the idea that, x is r cosine theta, y is r sine theta. And so that's where we start. And we just substitute in for x and y. Bless you. Bless you. And so essentially what we're doing for this, when we write polar equation, we're trying to get r by itself. That's all we're trying to do. So from here it's algebra, right? It's just algebra. And so go ahead and do that. Get the r by itself. Again, polar equations will end up with a r and a theta. Rectangular equations will end up with an x and a y. I should say or, not necessarily. What's the first move here? Yeah, factor out an r. Factor out an r, and then it's just a matter of dividing. And that's it. There's your polar equation of, I think, and we're going to get to the calculator for the very last problem, but I think because you can put your calculator in polar mode, if you entered this equation in and graphed it, and then if you put it back into, what's the other mode? Function mode, I guess, I think is what it's called in the calculator. You should get the same graph for that in function mode as you get for this in polar mode. That might be something. At 10 o'clock tonight, if you're not ready to go to bed yet, but you really want to keep working on math, Eliza, you can check that out and see if it works. All right, that's all you got to do for that one. Let's go the other way. Polar to rectangular. Let me give you a hint about what you should be doing, okay? You're trying to manipulate the equation to end up with either an r cosine theta or an r sine theta. Because then you can substitute an x in place of it, or a y in place of it, or an x and a y, right? That's what you're trying to accomplish. Get it to a place where there's just an r cosine theta and or just an r sine theta, so you can replace those with x and y. That's sort of the strategy. And so here's an example that we're going to go through. It seems pretty, no big deal. If you want to give it a shot, go for it. I'll give you a minute to try to see what you think you're going to do. Any thoughts about what you might try to do here? End up with an r cosine. Since this doesn't have a sign, what I need is an r here. But I have a 3. Can you just flip them and make this a 3, make that an r? Is that okay? Why not? Yeah, so it'd be 1 over r and 1 over 3 is not a big deal, but then it'd be 1 over r, not r. Maybe multiply both sides by r. Ding, ding, ding. You are correct. Good job. Multiply both sides by r, and that allows it to have an r. Cosine theta. Very good. What about this r squared, though? Because this is just x now. What am I gonna do with this r squared? How do I do with that?
X squared plus.
X squared plus y squared. Very good. Equals 3x. Well done. That's it. Okay, so that's not too bad. And now part 4. Part 4 is not bad. Like I said, it just takes time. because when we're talking about, we're talking about some crazy graphs. We're talking about ones with, like, that look like flowers, flower petals. They're cool looking graphs. The what? No, yeah, no, that's later. Yeah, so we call that, it has rose petals. Some have the little swirlies and things like that.
Like lima beans. Oh.
Yes, okay. So this is on page 240, okay? Please don't write it down. Please screenshot it and put it in. We've got circles. Do we have any French students in here? Oh.
Where's Izzy?
Yes. No, because I just refuse to call it a limacon. I'm not gonna do it. That sounds like something from Star Wars.
No, it's limaçon.
Limaçon. It's limaçon.
Like the little line.
And I don't even
under the
take
C
French.
Makes it, no, the little line under the C makes it an S sound.
Right. Son. But you gotta go son.
Like garçon.
And like,
It's a limaçon.
it's always, for me, French is so guttural. I just, it doesn't, I know sometimes it can sound like a beautiful, pretty language, but there's also a lot of like almost throwing up sounds going on in French. And that's one of those.
Have you ever heard a French person or a person with a French accent say refrigerator?
No, well, I don't know. Anyway, okay, so we're gonna talk about these three mostly. Obviously, circle, no brainer, easy peasy. It's going to be set up nice for us. If it is r times whatever the diameter times cosine, then it's going to be symmetrical with respect to the x-axis. Okay, so that means it's going to be. It's probably going to be shifted. It's not going to be centered on 0, 0. Same with this one, and now it's going to be symmetrical with the y-axis. We have our flowers, our rose petal curves. There's a couple things to keep in mind. The number in front is the maximum value. That's the biggest that the radius can ever be. N tells us how many petals there will be. If n is odd, there's that many petals. If n is even, there's 2 times that many petals. Okay? If it's cosine, it's going to be symmetrical with the x-axis. If it's sine, it's going to be symmetrical with the y-axis. And one of the things I will encourage you to do, I'm going to show you the very last problem. I absolutely encourage you to use your calculator to check your work, to see if what you drew was right. I don't encourage you to reverse engineer it. That's just kind of cheating. But we should have a general idea. Then we have a limaçon.
Lemon and salt.
Limaçon. It's limaçon. Whatever. Okay, I expect you to all be fluent in mathematical French by the end of the day. So A plus or minus B cosine. Okay, this again is the cosine's telling you x-axis symmetry, sine's telling you y-axis symmetry. It may have an inner loop, so it might loop around itself, not always. It may loop around, there may be a little pull, anyway. It gets all kinds of crazy looking things. Let's get into some of these problems and what it really takes to do. We're gonna do 2 by hand and 1 on the calculator. It's an evil laugh because this is kind of painful. It takes time again, and yes, I didn't assign you that many, but so this one is an example of the rose petal curve. Okay, it's going to have y-axis symmetry, symmetrical over about the y-axis. Since the number inside the parentheses with my angle is odd, there will be 3 petals. All right. And there's no, besides the calculator, it's making a table and coming up with a bunch of values and trying to understand how far the petals reach, how wide the petals are, when they come back to the origin, that kind of thing. That's what your problem solving involves, is how far do these petals go out, how wide do the petals get, when do they come back into 0 and end one of the petals, right? That's really what we're doing here. Now, do you want to just try this, or do you want to go through it together? And I'll explain the way I think through these.
Together.
Together? Okay. So, here's the way I think through it. All right. First off, I'm going to identify some things that I just mentioned. All right. One, that there are going to be 3 petals. So I know what it should look like. I know there should only be 3 petals in the end because of that number 3 in the middle. And I know that the max radius, I know we call it radius, but even though it's not a circle, but essentially the furthest away that a petal can get from the origin is 4. And to me, that's the best place to start. Where are the ends of all the petals going to be? And so in order for the ends of those petals to end up at 4, I need to know where they are 4. And so the question I have to ask myself is, when does the sine of 3 theta equal 1? Because if the sine of 3 theta equals 1, then I know r equals 4. Right? Because if this is 1, 4 times 1 is 4. So now we have to try to figure that out. So in your mind, you should be saying to yourself, all right, when does sine equal 1?
Because of the max thing, the max radius thing. That's fine.
Well, that's why we're checking 1. Because that's the only way for this to be 4, is when this equals 1. Because also think about what sine is. Sine can oscillate between -1 and 1, and it can't be greater than 1. It can't be less than -1. So we'll just focus on 1. That's basically the biggest value sine can be, is 1. So when does this happen? When is sine of an angle equal to 1? Yeah? Pi over 2. At pi over 2, the sine of the angle is 1. Okay? So in other words, I need to figure out when this equals pi over 2. Right? Because when is 3 theta equal pi over 2? Pi over 6? When else? Right? So that's one place. Right? For sure, pi over 6. That's one place where it will be 4. Okay? And notice, a magical point appeared at 4 and pi over 6. So I know that's the end of one of my petals. And since there are 3 petals, how many other angles should there be where the sine of 3 theta equals 1? Yeah, there should be 2 more. Well, we got to figure out where those are. How else can I get? So really what we're doing is going 3 theta equals pi over 2. So, right, that equals pi over 6. But when else? What other value can I stick in there for theta? Because this is, right, what other angle can I put in here that's going to make this equal pi over 2? We don't need to do negatives. We can just stick with positives. It doesn't have to just equal pi over 2. What else could it equal? Nope.
1. Oh, wait, 1/3. Wait, no, that's not 1. How do we get 1? Pi over 4?
Go around. Another 2 pi. Okay? So if 3 theta equals 5 pi over 2, it's still the same angle, right? Lands in the same spot. We just went around another time. But now if I divide that by 3, I get 5 pi over 6, and that's still fine. Right? That's still in my grid. Or what else am I going to have to use? So you got to add another 2 pi, which is just 4 pi over 2. So that's going to be 9 pi over 2. Okay. So what is this? What is 9 pi over 6? 3 pi over 2. And there are the ends of each of my petals. Okay. So when you have that number, that's how we create, I shouldn't say we, how those different petals are created. That's what this 3 does to the theta. it forces us to rotate around that many more times and then divide that number by 3 to keep it between 0 and 2 pi. And then, so in reality, I have a point 4 pi over 6, 4 5 pi over 6, and 4 3 pi over 2. Okay. So that's where all 3 of those come from, right? So I know that I have some kind of, and I'll draw just a quick little bad sketch, right? So that means I've got some kind of pedal-looking thing like this, some kind of pedal-looking thing like this, and something like that. Pretend that it actually hit the point. Okay, that's really what, by finding the endpoint, the maximum radii for this curve, we get a sense of what this shape is going to take. Okay. If you want to draw them, I drew these this way just to kind of go, okay, I have a sense now what this thing should look like. We're gonna get much more specific, and we're gonna do a much better job of it. But the thing is, each petal is going to be the same in terms of size. So I really only have to focus on one, and then I can use the information from one of those petals to get me to the other petal. All right. Now, so my next thing, the easiest thing to figure out, of course, is when sine of 3 theta equals 0. I need to know when it gets back. So again, if I'm thinking about it this way, it starts at 0, comes out, comes back around. So I need to know how kind of far or wide this can get. Because if I go here, right, that could be too wide. If it's like this, it could be too skinny. So we're going to get more information. That's really what I want to do. All right. Of course, we know that the sine equals 0 at 0, pi, 2 pi, 3 pi, 4 pi, and however many times you go around. Okay. So that way this one's a little easier to do. All right. And so if it's at 0, pi, 2 pi, 3 pi, you take that and divide it by 3, and that's where you come up with your angles that where it would come back to 0. So think about it this way, right? So here's what's happening with this radius in problems like this. Because as the angle is changing, the radius is changing. And so I'm going to try to draw this. It's going to be probably a bad drawing, but I'm going to do the best I can. So it's like I got a little short radius, and then we're rotating, it gets bigger, and rotating, it gets bigger, and we rotate some more, and it gets bigger, we rotate some more, it gets bigger, we rotate some more, it gets bigger, and that's as big as it gets. And then it starts coming back down. The radius starts shrinking as the angle is changing. As we are making that rotation around, the radius starts off really small, it's at 0, it's nothing, and it starts growing as we're turning, and we land at that point, at the end of the pedal. And then as we start rotating, it starts coming back down again. And so that's what's happening here, is we've got ends of the pedal, so it starts at 0, and then by pi over 3, it's back to 0. And then it moves back out to 2 pi over 3, and then it comes back down. So it starts at 0 here, and it starts working its way out to 4, and then at pi, it comes back down to 0. And then at 4 pi over 3, it starts at 0 and starts working its way back out to 4, and then it comes back down at 5 pi over 4. Okay, that's what's happening here. Think about that where the radius is involved is as you're rotating, the radius grows till it hits the max, and then it starts shrinking as it hits 0 again. And then it works its way around. That's really what's happening here, okay? Now, the next part that we have to do, and so what it's going to look like is something like this, all right? Notice here, I drew more specifically. It came back in at pi over 3. It did not pass the pi over 3. So it started off, and I know it's on the axis, but it's actually, it's really off the axis. Just there's 1 second where it's on the axis, and then it starts growing, and it grows and grows and grows as if it was sort of filled up with radii. And it doesn't expand beyond pi over 3. And then just that process starts all over again, okay? To be even more specific, we need to know where the widest part of that pedal is. And it would be helpful to know maybe something about pi over 12, because that's kind of in between. And maybe pi over 4, something in there, okay? And so, again, in order to get our best graph, what I'm going to do now is go, okay, let's look at pi over 12, because that orange, what I drew, is still not as accurate as it could be. Because I want to see what happens here at pi over 12. What's the radius? How far out does it go at this point? And how far out does it go at this point? I'm going to make a guess that those should be the same. Okay? And so what we're trying to then do is find the sign of, when I plug pi over 12 in, it's really sine of pi over 4, right? Because 3 times pi over 12. And then the sine of 3 times pi over 4 is the sine of 3 pi over 4. Well, 3 pi over 4 is 135 degrees. Sine of 45 degrees. Those signs have the same value because y is positive, right? So y is positive here, y is positive here. So when I plug these in and I get pi over 4 and 3 pi over 4, these values will be the same. And so, of course, the sine of 45 degrees is just 2 times the square root, which is, not quite 3-ish, right? It's probably, I don't know exactly what the value is, probably 2.8 or something like that. So what that's telling me here, and so see how I graphed it, at pi over 12, I'm at 1, 2, and like 2.8. Yeah, I guess I was right. And then over here, it's 2.8. So I'm now confident that that's probably as wide as the pedal is going to get. And that took a lot of work to get there, right? It took a lot of understanding and trying to interpret what could happen at those particular angles. And then once we do that, we can safely say that it's going to be that pedal, since we know that it's going to come back down to 0 at pi over 3. So notice here what's going to happen is this pedal is going to shoot out here and then eventually kind of come back in. It's going to shoot out here and eventually come back in. And I think at this point we can confidently now do the same idea. It's gonna be that wide over here. So I'm gonna have 2 points, one here and then one here, and then we can just draw the rest of the pedals in. All right. So I end up with, and so I went ahead and drew, the same wide-ish points of each of the pedals, and then from just connect them up. And that's a much better, I probably drew that 3 or 4 times before I felt really good about it. And it's obviously it's not going to be perfect, okay? But if you notice here, it does bump out beyond here, right? It does bump out, and then it comes back in, and it's almost tangent to this line at pi over 3. So it does kind of come out, but it gives me some idea of shape. Okay. All right, we got to get moving because the Limaçon is gonna go. So we got to draw that, and then the last one is going to be a calculator. Okay. So I know that it's a Limaçon because there's the 3 sine or the 3 cosine or and then you have a number added or subtracted in the front. Okay, that's how I know it's going to be a Limaçon. And so what I'm going to do the same kind of thing. We're going to start getting a basic skeletal version of it, get an idea what it should look like, and then we're going to get into it pretty in-depthly to come up with it, because the places where this thing curves and pivots and changes direction, it happens much more often. All right. The first thing that I know is that because this has a sine in it, it's going to be symmetrical to the y-axis. Okay. So So it's going to be, it's going to have y-axis symmetry, which is going to be important. So we know that we have a general sense of direction. Now I'm going to approach this the same kind of way in terms of how to get our well, actually, that's not quite accurate. I want to find out a couple things. Okay, what is the maximum? What's the maximum radius that we can have for a problem like this? For this particular problem, how big could our R be?
3?
No. What's the biggest value for sine of theta? 1. So what's the biggest value for R?
Oh,
6, right? So this would be 3 plus 3. So the biggest this could ever be is 6. Okay. At some point, is it possible for this to ever be 0? What would have to occur for this to equal 0? Sine is -1, okay? And that happens at 3 pi over 2. Could it ever just be 3? Because when is sine 0? Pi and 0, okay? So let's focus on those first. Those will make, those are easy ones to kind of deal with, okay? So let's start with when it's going to be the one we just ended on. We just set it, since there's no number inside there with theta. When theta is 0, when theta is pi, the radius is 3. Okay, we talked about the biggest possible value. And the smallest possible value. So what is the value of sine when r equals 6? In other words, when does sine equal 1? Pi over 2. Okay. And then, like we talked about, it's -1 when it's 3 pi over 2. Why didn't I? Oh, yeah, I did graph it. You just can't really see it there. Okay. So those are the easiest ones to start with. Okay. Because those are the easiest values of sine. At zeros, at 1, at -1. And so really rough, and this is a bad sketch. But again, I'm going to draw this just like we did the rose petal one to give you a sense of what we're going for. We should end up with something that looks like that. With only 4 points, we can't guarantee how accurate a sketch like this is. But we should have something like this. We don't know if it's going to fold in on itself and have a swirly in it or any of that kind of stuff until we test a bunch of more. And that's what we'll do next. Okay? All right, what's the next easiest value of sine? Ending value of sine, I guess. We eliminated 0, we eliminated 1, we eliminated -1. What's the next probably easiest value that you could get for sine? That's not a crazy, ridiculous decimal. 1/2, right? We can get sine to be 1/2, right? When is sine 1/2? Pi over 6. When else is it 1/2? 5 pi over 6. So if this is 1/2, what's r? So we got 3 plus half of 3. Well, what is that? That's 4.5. Okay? So at pi over 6 and 5 pi over 6, the radius is 4.5. Okay, so right away I know, okay, my little sketch was too skinny. This one's fatter than that. Okay? From here, it's kind of up to you to pick what you want to pick. There's nothing really nice after that, other than if we said, okay, pi over 3 and 4 pi over 3, no, 2 pi over 3, then I know that's square root of 3 over 2, and I could use that. Like, there aren't really good ones left. I mean, I guess you could look at 45s too, square root of 2 over 2s. At this point, I'm going to the calculator. I'm like, I need to start punching stuff in to try to figure out what these values should be. Okay? And that's what I did. And to save you some time and trouble, I did use pi over 3. 2 pi over 3. And then I did a whole bunch of other ones. Okay? So just to show you what I did. Okay? So pi over 3, this is the square root of 3 over 2. I plugged that in, figured that out, and that got me about 5.6. And so that's both of those. Now it's starting to really take shape. Okay? Then I also looked at 7 pi over 6 and 11 pi over 6, which would make this negative 1/2. So that's where this 1.5 came from. And then I worked off of these two as well. And again, I did that on the calculator. So this is what I'm saying about it's going to take some time. Because there are only so many nice trig values that you can use. Right? And obviously, I made a ridiculously gigantic table. And when you're doing a lemon somme by hand, that's what it takes. Okay? And so now I've got a pretty good idea what this shape really does look like and how wide it is and how curvy it is and that kind of thing. And try to draw our sketch as best as you can, and that is as best as I can get. These points all came from, I wanted to use 30s and 60s, in versions of 30s and 60s. So I wanted to use versions of pi over 6s and versions of pi over 3s. And so when I started off originally, I just started with the one that would make this 1/2. That's how I came up with the pi over 6 and the 5 pi over 6. My next best option, now I guess I could have then gone right away to 7 pi over 6 and 11 pi over 6 and found out negative 1/2. That's where the 1.5s came from. And then my last resort was to use the 60s versions, which is square root of 3 over 2, which is like 0.8660 or something, and you do the math and come up with those.
So like for the
But you could I guess what I'm saying is I'm working from the angle first. I'm using the angle because I know that I'm going to have to plug that in to find the length of R. You could pick any angle you wanted. I was just picking ones that we're generally most familiar with. All right, and then this is the last bit, is doing it on the calculator. Now this looks like an English word to me, and I don't know if you say it. Lemniscate. Is that what you said? I don't know. If you want to make it French, you just go "hon" at the end, and then it's French. Just kidding. I always like telling that to Miss Benitez. She doesn't. She just kind of rolls her eyes at me. All right. So what's important? We're just going to graph this on the calculator. Put your calculator in polar mode. So hit the mode button. And then, yeah, you're still in radians. So yeah, I was right, function. So we're going to go to polar mode. And then when you go to your y equals screen, it's not going to be a y anymore. It's going to be an r. Okay? And so we can just enter that in. So here's the issue, right? This is r squared. There's no r squared. So what are we going to do here? Yes and no. We have to have a plus or minus, which means I need how many equations? 2. I need one of them to be positive and one of them to be negative. And then, and you can actually, if you want to, you don't have to, because when the calculator draws this, it will draw it in 2 different colors, right? Because on your calculator, you probably have, one of them red, one of them blue. You can change the colors if you really want to and make them be the same color if that bothers you at all, okay? So that's important, making sure we do that on a something like that with the r squared. The other thing that I think is helpful is Zoom Fit, which is on your calculator, Zoom 0. And so instead of it being the standard 10 by 10 window, it will create a window that fits your graph, that your graph fits to. That's a better way to put it. The window that your graph will fit to. And then it's just a matter of drawing it out. Sketching it, and you get a crazy swirly thing like that. And you can trace it and find points off it if you need to, if it's asking you for anything, but I just want to make sure you know how to do that on your calculator.